Hi, today we would like to learn about mechanical filter. A mechanical filter uses a resonant vibration of the mechanical disc to provide the selectivity. Used in the intermediate frequency amplifier of highly select super heteroid receiver is also known as mechanical wave filter. From this figure, we can see that we have the disc of the mechanical disc 1, 2, 3, 4, and this mechanical disc will be vibrate with each other when the voltage is supplied. And due to the electromagnetic field of this magnetic not and sound and vibrate the mechanical disc and will generate the frequency. Next, we will learn about crystal and ceramic filter. Crystal and ceramic filter are made of kind silver of course crystal for a certain other type of the ceramic material. Crystal and ceramic elements are widely used in the oscillators to set the frequency of the operation to a precise value. And these crystal and ceramic elements are used as the circuit element for the filter and specifically bandpass filter. This is the figure of the crystal filter, and we can see for a crystal filter, the first one, A, is the equivalent circuit. We have the R, resistor, L, inductor, C is our capacitor shunt, and CP, our capacitor in parallel. And this is the symbol for the B, is the symbol of crystal filter. When the voltage applied to our filter, our crystal filter, we will have the voltage become the pressure on the piezo on the crystal filter, and this will induce the piezoelectric effect. And this piezoelectric effect will be vibrate the materials of the filter and generates the frequency to be filtered. The frequency range that used to be the filter. Okay, this is the quasar of crystal apply of the voltage, and it will cause the impedance here and mechanical mass of the quasar. And from here, we will have the frequency from the capacitor with the L and generates the series resonant frequency. And this series resonant frequency will have the frequency generate until Fs in this Z impedance with respect versus our frequency, and this can be calculated by using the frequency resonant frequency. Fs equals to 1 over 2 pi square roots of Ls, our inductance and capacitance in series, and also our Rs. And then this circuit will induce the frequency during the inductive effect by the L. And Then it will influenced by the parallel resonant frequency from the capacitor parallel and will generate the Fp. And this Fp can calculate from 1 over 2 pi square root Ls, and C is the equivalent to achieve the equivalent capacitor. And we can see from here, and our equivalence capacitor is equal to Cp Cs in series divided by Cp plus Cs. And this equation actually is the capacitor voltage divider. Now we go to ceramics. And from here, this figure is the ceramics filter look like. Okay. And from the ceramic filter, it generate the RG. Okay. And also, and it has three. One is the input and the output to the RL resistor load, and also another one leg is to our ground. And the vibration in the ceramic will generate the frequency, and ceramic filter normally is used for the intermediate frequency for the transmitter and the receiver. Now we go to surface acoustic wave filter. The surface acoustic wave filter SAW filter is a special form of crystal filter and is designed to provide the exact selectivity required by a given applications. SAW filters are normally used at a very high radio frequency where selectivity is difficult to obtain. They are widely used in the modern TV receivers, radar receivers, wireless, lens, and cell phone. Okay, this is the surface acoustic filter. Okay, surface acoustic filter, we will have the input to the interdigital transducer, and at this interdigital transducer, they will generate a surface acoustic wave on the piezoelectric ceramics effects, and this surface acoustic wave will transmit to the interdigital and filter interdigital transducer at the output side. So it will generate the frequency from the piezoelectric ceramic effect. Switched capacitors filters. Switched capacitor filters, SCF, also known as analog simple data filter or commutating filter, are active IC filters made of op-amp capacitors and transistor switch. They provide a way to make turn or selective circuits in an IC with out the use of discrete inductors. Capacitors or resistors, the secret to the SCF is that all the resistors are replaced by the capacitors that are switched by the MOSFET switch. And we can see here all the capacitor and resistor are replaced by the capacitors. And this capacitor is the MOSFET switch. Okay, from this figure A is the conventional inductor, and this conventional inductor has the resistor of R, and this resistor of R will be replaced by the MOSFET switch. Okay, and this MOSFET switch will be on and off to generate two phase. For the S1, it will on and off to generate for the phase 1. For the phase 2, it will on and off to generate the signal for the phase 2. Okay, so now we go to the calculations of the switches capacitor back filter by compare the A conventional integrator and the switches capacitor integrator. We will have the A, the current I is calculated from V1 minus V2. So we will have V1 here and our resistor V2, and this will compare with another V1. Okay, now this one we will have the switch and also the switch for the MOSFET switch and also the capacitor. So we will have, okay, I draw it simple, switch, capacitor, and here is V2. And we are comparing A and B. Okay, so here we assume that V1 is bigger than V2. Okay, so at T1, okay, our phase 1 will have a high as S1. So this one is our S1. This one is our S2. Okay, it will S1 will when S1 is on, the phase 1 is high, which means this one. Phase 1 is high when it's on. Phase 1 is high when S1 is on. Okay, C will change up to V1, voltage 1. At the T2, our phase 2 is high, so our S2 is on. C will charge up to V2. And we see here, when our S2 is on, okay, our phase 2 is high. Okay, it will charge the C2. And up to V2. And the changes of the electric charge Q is equals to our capacitor V1 minus V2, and we can use our current equivalent equals to charge divided by the time, and C V1 minus V2 divided by our T clock, and this is our T clock, the repetition of one cycle of time in clock. And 1 over t time in clock will be equal to f, frequency in clock. So we will have frequency clock multiplied with c multiplied with v1 minus v2. And we know that we have a Ohm's law. Current equivalent will be equal to V1 minus V2 voltage divided by resistor in equivalent. Then we will have F clocks dot C, okay, V1 minus V2, okay, equal to V1 minus V2 and divided by R equivalent. And here we substitute these equations into the I, okay, and we simplify it, the C, and uh, we simplify our V1 minus V2 and V1 minus V2, and we'll get our frequency clock is equal to 1 over R equivalent C capacitor. So here is the principle of operation. We stimulate the R equivalent, resistor equivalent, by charging and discharge the capacitor between two voltage levels. Okay, by building this capacitor filter, we will build this switch capacitor filter by replacing this R equivalent. Okay, and this figure is actually a RC low pass filter. By replace this R equivalence with the physical resistor with the equivalent switch capacitor resistor. So which means is here we will replace with switch 1, switch 2 and capacitor. And after replace, we will have the frequency as 3 dB bandwidth is omega at negative 3 dB, which means is our cut-off frequency will be equal to 1 over our equivalent C2. And now this thing will be equal to our Fs C1 divided by C2. And for this equation, our frequency cut-off frequency will be equal to 1 over 2 pi Fs multiplied with C1 divided by C2. Okay, now we go to Switched capacitor filter, and here we will have an input, and this one actually is a commutating switch capacitor filter, and we will have an input of R, C. Here is our switched capacitor, and this switched capacitor is in cascade, so it's a commutating of the switches. So each switch 1 indicates signal for number 1, switch 2 indicates S2 here, switch 3 indicates S3 here, and switch 4 indicates here. And for this one, actually is a band pass filter. So we will have a output of frequency output equals to Fc divided by N, and the bandwidth equal to 1 over 2 pi N RC. And here is a number of your RC. Okay, that's all. Thank you. So remember to like and share my video. Thanks. Bye.